There is a number that came out of CATL's Yichang production facility in 2023 that the battery industry has been quietly stress testing ever since. $39 per kilowatt hour. That is the certified manufacturing cost for sodium-ion cells rolling off a commercial production line. Let me tell you what that actually means. Lithium-iron-phosphate, the cheapest lithium chemistry in mass production, sits around $80 per kilowatt hour. Sodium just cut that in half. You heard that right. And here is the part that blows most people's minds. That cost figure is not the story. The story is the 30-year-old material ceiling that had to be demolished to get there, and what that demolition means for every electric vehicle, every grid storage project, and every mining operation on Earth. Hit subscribe so you do not miss the next one. By the end of this video, you are going to understand exactly how they broke it. In 2021, CATL stood in front of the global battery industry and announced it was going back to sodium. The room, figuratively speaking, did not applaud, it calculated. And what most analysts calculated was that sodium-ion had already been given a fair trial, had already failed that trial on the numbers that mattered, and that revisiting it was an exercise in wishful thinking dressed up as engineering ambition. To understand why, you have to go back further than 2021. You have to go back to the 1980s, when sodium-ion and lithium-ion were genuinely competing chemistries, two parallel bets on how to store electrical energy in a rechargeable cell. Both use the same basic principle, ions moving back and forth between two electrodes through a liquid electrolyte. The difference was the ion doing the moving, and that difference turned out to matter enormously. Lithium ions are small, sodium ions are not. A sodium ion carries a radius roughly 34% larger than a lithium ion, and in battery chemistry, size is not a minor detail. It determines how easily an ion can squeeze into the crystal lattice of the electrode material, a process called intercalation. Picture a standard door frame. Lithium ions walk through it without touching the sides. Sodium ions have to turn sideways. And at the speed and volume that a rechargeable battery demands, turning sideways means the frame starts to crack. That cracking, the mechanical stress on electrode materials caused by sodium's larger dot, translated directly into the number that ended sodium's first era. Energy density, the amount of energy you can store per kilogram of battery. By the early 1990s, lithium-ion cells were demonstrating above 200 watt-hours per kilogram in laboratory conditions. Sodium-ion cells were stuck below 150. The gap was not marginal. It was the difference between a technology that could power a laptop or an electric vehicle and one that could not. Here is the detail that most histories of battery development leave out entirely. The industry did not abandon sodium because sodium was chemically flawed. It abandoned sodium because lithium was better, and once the investment followed lithium, the gap widened every year. Argonne National Laboratory, the European Battery Alliance, and the major Japanese battery consortia all directed their materials research budgets toward lithium chemistries through the 1990s and 2000s. 30 years of compounding improvement, hundreds of billions of dollars in supply chain infrastructure. Lithium-ion did not just win the 1990s. It built a wall around itself, one patent portfolio and one gigafactory at a time. By 2021, that wall looked permanent, and that is exactly what made the announcement that came next so easy to dismiss. In July of 2021, CATL published the specifications for its first-generation sodium-ion cell and announced it would reach commercial production within 2 years. Stated energy density, 160 watt-hours per kilogram. Stated goal, close the gap with lithium-iron-phosphate far enough to make sodium viable for entry-level electric vehicles and grid storage applications. The reaction from the analyst community was swift, specific, and almost uniformly skeptical, Bloomberg EF flagged the energy density shortfall immediately. At 160 watt-hours per kilogram, CATL's first-generation cell sat roughly 20% below the commercial LFP benchmark. That gap, the analyst noted, translated directly into vehicle range, and range was the single metric that determined whether a consumer bought an electric vehicle or walked back to the gasoline forecourt. Panasonic's battery division quietly noted that their own sodium research, shelved in 2004, had hit similar numbers before they concluded the intercalation problem could not be solved at acceptable cost. Institutional consensus settled somewhere between polite interest and confident dismissal. The specific technical objection was cycling stability. Sodium-ion cells had a known failure mode, capacity fade. After repeated charge and discharge cycles, the electrode materials degraded faster than their lithium counterparts. Early sodium cells were losing measurable capacity within 500 cycles. A consumer vehicle battery needs to hold above 80% capacity for at least 1,500 cycles to be commercially warranted. The gap was not a rounding error. They said the same thing about lithium-iron-phosphate in 2005. We all know how that ended. LFP chemistry was formally dismissed by the majority of the Western battery industry on almost identical grounds: lower energy density than the premium lithium chemistries, questionable long-term cycling, and a cost structure that looked attractive on paper but had not been proven at gigafactory scale. By 2024, LFP accounted for more than 40% of all EV battery shipments globally. The dismissal was not wrong about the first-generation cells. It was wrong about what the program was actually for. What CATL was running between 2021 and 2023 was not a commercialization push. It was a materials research program with a commercial deadline. The first-generation cell was a public proof of direction, not a finished product. Actual work was happening at the cathode and the anode simultaneously, two separate materials problems that had defeated every prior sodium-ion program, and CATL had decided to attack both of them at once. What that attack looked like is where the story really begins. The cathode is where sodium-ion chemistry had always broken down first. Not because sodium could not store energy in a cathode material. It could. The problem was what happened to the cathode material after the 500th time sodium ions pushed their way in and out. Crystal lattice structures of conventional sodium cathode materials, layered metal oxides, primarily, would begin to deform under the mechanical stress of repeated cycling. Ions moving in and out of a rigid crystal structure at volume is not a gentle process. It is closer to hammering a nail into the same hole several thousand times and expecting the wood grain to hold. The material CATL identified as the solution was not new. Prussian white, chemically an iron hexacyanophorate framework, had been studied as a sodium cathode candidate since the 1980s. Researchers knew it had structural properties that made it theoretically well-suited to sodium-ion cycling. Its framework is open and built around channels wide enough to accommodate sodium's larger ion without the same mechanical stress that destroyed layered oxide cathodes. Those channels do not just tolerate sodium ions moving through them, they are shaped for it. The problem was water. Prussian white, synthesized under standard laboratory conditions, absorbed water molecules into its crystal structure during formation, a contamination the industry called crystal water. At concentrations above roughly 2% by weight, crystal water destabilized the lattice during high-temperature cycling, accelerating exactly the kind of capacity fade the critics had flagged. Every prior Prussian white cathode program had run into this wall. What looked right on paper kept degrading in practice, and the degradation traced back to water content that standard synthesis processes could not eliminate. The part that almost never makes it into the public reporting is what CATL actually institutional consensus settled somewhere between polite interest and confident dismissal. The specific technical objection was cycling stability. Sodium-ion cells had a known failure mode, capacity fade. After repeated charge and discharge cycles, the electrode materials degraded faster than their lithium counterparts. Early sodium cells were losing measurable capacity within 500 cycles. A consumer vehicle battery needs to hold above 80% capacity for at least 1,500 cycles to be commercially warranted. The gap was not a rounding error. They said the same thing about lithium-iron-phosphate in 2005. We all know how that ended. LFP chemistry was formally dismissed by the majority of the Western battery industry on almost identical grounds: lower energy density than the premium lithium chemistries, questionable long-term cycling, and a cost structure that looked attractive on paper but had not been proven at gigafactory scale. By 2024, LFP accounted for more than 40% of all EV battery shipments globally. The dismissal was not wrong about the first-generation cells. It was wrong about what the program was actually for. What CATL graphite is the standard lithium-ion anode. It works because its layered carbon structure has an interlayer spacing of 0.335 nanometers, a gap that lithium ions, with their radius of 0.076 nanometers, can slip into and out of cleanly across thousands of cycles. Sodium ions carry a radius of 0.102 nanometers. Graphite is the standard lithium-ion anode. It works because its layered carbon structure has an interlayer spacing of 0.335 nanometers, a gap that lithium ions, with their radius of 0.076 nanometers, can slip into and out of cleanly across thousands of cycles. Sodium ions carry a radius of 0.102 nanometers. Trying to insert a sodium ion into graphite's interlayer spacing is like trying to park a delivery van in a space marked for a compact car. You can apply enough force to get it in, but the structure around it deforms, and after enough repetitions, the structure fails. Every anode material the sodium-ion field had tested through the 2000s carried some version of the same problem. Either the spacing was too tight, or the material that could accommodate sodium's larger ion degraded too quickly, or the cost of synthesizing it at scale was prohibitive. The field had produced a long list of theoretically interesting candidates and a much shorter list of materials that actually worked in a commercial cell. CATL's answer was hard carbon, a disordered non-crystalline carbon structure produced by pyrolyzing organic precursor materials at high temperature. Unlike graphite's regular layered geometry, hard carbon is deliberately irregular. It contains voids, defects, and nanopore structures distributed throughout the material, and those irregularities are not a manufacturing flaw to be engineered out. They are the storage mechanism. Sodium ions nest inside the defects and nanopores during charging, rather than intercalating between ordered layers. The disorder is the point. It sounds like it should not work. That is exactly why it does. The specific capacity of CATL's hard carbon anode reached above 300 milliampere-hours per gram in published testing, a figure that matches or exceeds the graphite anode performance in standard lithium-ion cells. The key variable that made it reproducible at scale was pyrolysis temperature control. Consistent defect density across a hard carbon anode requires holding synthesis temperature within a narrow band during production. CATL's process holds that band to within 5 degrees Celsius across industrial-scale batch runs. Consistent defect density at scale. That sentence is worth reading again slowly. Both mechanisms now worked. The question was whether they could be made to work together reliably across millions of units at a cost that changed anything. Two breakthrough materials do not automatically become a breakthrough battery. This is the part of the engineering story that almost never gets covered. The gap between a cell that works in testing and a cell that works in a factory, in a vehicle in January, in a country where the temperature drops to minus 40 degrees Fahrenheit and stays there for 3 months. The conventional approach to sodium-ion manufacturing had always been adaptation. Take a lithium-ion production line, modify the electrode coating processes, swap in the new materials, and run the same basic assembly sequence. Sodium-ion cells, however, have genuinely different environmental requirements at several critical production stages. Prussian white cathode material is sensitive to atmospheric moisture in ways that standard lithium-ion cathode materials are not. Adapted lines introduced contamination at the coating stage, the same crystal water problem that CATL had solved in synthesis showing up again in manufacturing. CATL did not adapt a lithium-ion line. They designed the sodium-ion line from the electrode coating environment outward, building moisture control into the production architecture rather than adding it as a post hoc safeguard. The dry room specification for sodium-ion production is less stringent than lithium-ion at the cell assembly stage because the Prussian white cathode, once correctly, tolerates ambient conditions better than lithium nickel manganese cobalt oxide, while being more stringent at the cathode preparation stage, where moisture exclusion is absent. That inversion cut dry room energy consumption by approximately 30% compared to an equivalent lithium-ion line. Now here is the part that changes everything about how you think of sodium-ion as a commercial proposition. CATL did not bring it to market as a standalone replacement for lithium. They brought it as a system. The AB battery concept pairs sodium-ion and lithium-ion cells within the same pack. CATL CTP, Sendern-Ling cell-to-pack architecture, integrates both cell types into a single structural module. The Yichang facility reached 20 gigawatt-hours of annual sodium-ion production capacity by late 2023, enough to supply packs for roughly 2 million entry-level vehicles per year. Not a pilot line, a gigafactory. The number that came out of that factory required a second verification before anyone would publish it. Here is the honest picture. Sodium-ion is not lithium-ion. At the cell level, CATL's second-generation sodium-ion chemistry delivers approximately 160 watt-hours per kilogram. Lithium-iron-phosphate, the cheapest lithium chemistry in commercial production, delivers approximately 200 watt-hours per kilogram. That 20% energy density gap is real. It is acknowledged by CATL's own engineering team, and it means that a sodium-ion pack delivering equivalent range to an LFP pack will be physically larger and heavier. For long-range premium vehicles, that trade-off does not close. The engineers know it. The honest version of this story includes it. Now here is what the certified result actually showed. Wood Mackenzie and Bloomberg NF independently confirmed CATL's production cost for sodium-ion cells at the Yichang facility, $39 per kilowatt-hour at commercial scale. The current floor for lithium-iron-phosphate in mass production sits at approximately $80 per kilowatt-hour. That is not a slight cost. That is a 51% reduction in the single largest cost component of an electric vehicle. At $39 per kilowatt-hour, the battery pack in a short-range urban electric vehicle costs less than the steel and aluminum in the body around it. Price stops being the battery's problem. Price implications landed immediately in the Chinese domestic market. Both the Chery iCar and the Jack Yiwei, configured with sodium-ion packs in the 100 to 150-mile range, entered production in early 2024 at retail prices below $15,000. Production vehicles, at scale, at a price point that lithium chemistry had never reached without significant government intervention. The low-temperature performance figure is the one that most analysts are not tracking closely enough. So, at minus 40 degrees Fahrenheit, the operational threshold for vehicles in northern regions of China, Canada, and Scandinavia Sodium-ion cells in the AB architecture retained 90% of rated capacity. Lithium-iron-phosphate at the same temperature retains approximately 60%. That 30 percentage point gap is not a marginal cold weather improvement. It is the difference between a vehicle that works in winter and one that requires a heated garage. Okay? The cobalt and nickel content of the sodium-ion cell is 0. Eliminating both materials reduces the mining footprint per kilowatt-hour by an estimated 40% compared to NMC lithium chemistry, based on life cycle analysis published by the Faraday Institution in 2023. If the cost figure surprised you, the next part is going to be even harder to believe. Hit subscribe so you are there when we cover it. That is not a cheaper battery. That is a different cost floor for the entire global energy storage industry. And the consequence of that moves far beyond any single vehicle or any single market. And to understand what a cost floor shift means for a global industry, you need to understand how exposed that industry already was before CATL sodium-ion line reached commercial scale. The International Energy Agency's 2023 Battery Supply Chain Report projected global battery demand reaching 4 terawatt-hours per year by 2030. 4 terawatt-hours, more stored electrical energy than the entire world, deployed in all battery applications combined through 2015. That figure assumes the lithium supply chain can scale fast enough to meet it without structural price dislocations. The assumption did not survive contact with the data already available when the report was written. Between 2020 and 2022, lithium carbonate prices moved from $6,000 per metric ton to $80,000 per metric ton, a 13-fold increase in 24 months. By mid-2024, prices had corrected back to approximately $13,000 per metric ton. The correction did not reassure battery makers. It confirmed their worst planning scenario. The cost of their most critical input could move by a factor of 13 within a single product development cycle. No factory financing model survives that kind of volatility without a hedge. Sodium carbonate, the feedstock for sodium-ion cell production, trades at approximately $150 per metric ton. It has never spiked. Production spans every major industrial economy on Earth, and reserves are effectively unlimited at any demand scale the battery industry could generate across the next 50 years. That is not a cost advantage. That is a supply chain architecture that does not require a hedge. Here is what most analysts are not tracking yet. The application where sodium-ion's combination of cost and low-temperature performance matters most is not the passenger vehicle. It is stationary grid storage. At sub $40 per kilowatt-hour, sodium-ion is now the cheapest viable chemistry for 4-hour grid storage installations. The duration, the class that utilities use to manage the evening demand peak after solar generation drops off. Heine Battery and BYD have both announced grid storage deployments using sodium-ion chemistry with combined announced capacity above 2 gigawatt-hours as of early 2024. The historical parallel worth studying is the transition from lead-acid to lithium-ion in consumer electronics between 2000 and 2010. Lead-acid had held the portable power market for over a century. When lithium-ion crossed the cost threshold, the transition took less than 8 years. Cobalt and nickel producers are now facing a structural demand question, not a cyclical one. The ceiling that governed battery economics for 15 years was never a chemistry law. It was a materials problem, and the global sector that built itself around one answer to that problem is only beginning to work out what the new answer costs to ignore. The sodium-ion story is not really a battery story, it is an access story. For 15 years, the cost floor of lithium-ion chemistry quietly determined who could participate in the electric transition and who could not. It determined which cities could afford grid storage and which could not. It determined which vehicle price points were reachable and which existed only in press releases. The engineering ceiling and the access ceiling were the same ceiling, and they both just moved. That is not a footnote in the history of energy storage. That is the headline. If you made it this far, you now understand more about why battery chemistry determines who gets clean transport than most people who write about this for a living. What was actually proven here goes beyond a single production cost figure. CATL demonstrated that a 30-year-old materials ceiling, one the industry had, treated as a permanent physical constraint, was in fact a geometry problem in disguise. The sodium ion was not too large for a battery. It was too large for the materials the industry had built around lithium. Change the materials, attack the crystal water in the cathode, engineer the defects into the anode, and the constraint dissolves. The chemistry was never the wall. The wall was the assumption that the materials were fixed. That finding travels far beyond sodium ion. Every engineering ceiling that has been standing long enough starts to look like a law of nature. Most of them are not. Most of them are the accumulated consequences of early decisions that optimized for a specific material, a specific ion, a specific production process, and then locked in through decades of compounding investment. The ceiling feels permanent because the investment behind it is real. But investment is not physics. And the teams that treat a materials ceiling as a geometry problem rather than a chemistry law have a long history of being right at exactly the moment the consensus is most confident they are wrong. If this changed how you think about where battery technology actually goes next, hit that like button and subscribe so you never miss what comes next. Now, I want to hear from you in the comments. Do you think sodium ion will displace lithium-iron-phosphate as the dominant EV battery chemistry within a decade? Or will lithium's energy density advantage keep it on top for the long run? Both sides of that argument have real engineering behind them. Drop your answer below.